Okay, so back again to power electronics. This is module number 3, week number 8. It's about inverter and AC controller or AC voltage controller. Today we will start with DC to AC inverters. We will discuss single phase. This week we will focus on single phase. Next week we'll start with 3 phase to have the full picture. And as introduction, you know, as I mentioned, single phase, we will talk about pulse width modulation inverter, square wave inverter, voltage concept, different type of inverters. We will go through the different circuits, their operation, their waveforms and formula, will drive formula. We will focus here more on harmonics. Harmonics is important issue need to be considered when we design inverter. Now, you know, most of our loads are AC loads, okay? So if you go to the application at home, in enterprises, companies, buildings, and so, you will find our load are AC, mainly air conditioning, let me say, which are the in motors, light, sets, different appliances, TV set, receivers, computers, tab, and these issues. So all these equipments use AC voltage. But what you know, we have in our AC voltage is fixed, constant. As example, when we come to Oman, we have 230 volt, 50 hertz. When we go to America, 100 volt, 60 hertz, as example. Okay, we cannot change it. Some application we need to change to get different function. As example, if I have motor in industry, okay, and I want to control it to have different products. The characteristics of the operation of the motor will give me different products because it gives me different function. How can I control the frequency? How can I control the voltage? Inverter will help me to do this. Have a look. This is simple circuit used in, it's called switch mode inverter, used to drive AC motor. My load here is AC motor, and my conventional input is AC input. Okay. Now I put here diode rectifier. Okay, diode rectifier, what would give me? Would give me DC. Okay, here is DC, here is AC. Okay, capacitor, you know, to smooth the voltage, and then the voltage, the DC voltage, will be input to this inverter, switch mode inverter. And then I got AC. You may say, okay, if we have here AC, we back to AC. What is the point? The point is the AC here is different from the AC here. Here I can't control, but here I can control. I can change the frequency, I can change the voltage, both, as we are going to discuss soon. Now this circuit is available in industry, it's used a lot, but one point need to be mentioned here, that power flow will be only from the supply to the load. Why? Because here we have diode rectifier and control rectifier. We cannot control it. But if we use control one, as you can see here, we have here thyristor or transistor control one, then this circuit will work in either direction, either in this direction or in this direction, which is useful because sometimes I need to do electrical braking for my motor, as we are going to discuss later, inshallah. So this is the switch mode DC to AC inverter. Mainly it converts into AC. Now, by the way, I mentioned that we put the capacitor here to smooth the voltage. Sometimes they put the inductance rather than the capacitor. It's DC link between inverter and rectifier. So when we put in inductance, we call it voltage current I source inverter, or current C, current source inverter. But when we put capacitor, we call it voltage source inverter. It's close to each other, but for the inductance, we focus more on smoothing the current for specific applications, while for the inductor capacitor, we smooth the voltage for specific applications. Now we will discuss the voltage source inverter, which is not, that much different from current source inverter. Now we have to categorize them. So if we want to classify them, we will classify them into 3 types. The first type is pulse width modulation. We talk about pulse width how we control the on and off, to control the pulse width. Then they control the switch operation. Then we control the output of the DC-DC converter. If you remember, boost, it has been discussed before. Now the same thing, almost the same thing we use here, pulse width modulation technique, okay, to control the output of the inverter. Here the input voltage, it could be battery, DC battery as example, constant. But we control it by pulse width modulation to control the magnitude and the frequency, both. Another one is the square wave inverter. In square wave inverter, okay, we have to control the DC input to control the output, okay? Now, last one is single phase inverter with voltage cancellation. Now, just a minute here, it is single phase. Does this mean it is not applicable for three phase? Yes, correct. It is not applicable for three phase, it's only for single phase. And voltage, it seems to be that we are going to cancel some voltage or part of the voltage. Yes, correct. This is what we are going to discuss later on. Now here, we can control the magnitude and the frequency also by controlling, as I mentioned, the cancellation, as we are going to discuss. Now today's session, I will just try to make introduction to the inverter circuits, talk about harmonics, about modulation, about parameters, the terminology used in inverter, and next session, inshallah, we will continue with this to discuss the single phase full bridge inverter. Now here is my converter, my inverter here, as you can see here, one phase switch mode inverter plus its filter. Now my input is DC, as you can see here, VDID, as we discussed for rectifier or for DC-DC converter. What is coming to the as input to the inverter is DC. My output is AC, VO, As you can see, instantaneous, it means AC. Now first, I will talk about one leg. This is one leg, leg A. As I discussed before in DC-DC converter, have a look here. This is a switch TA positive, which is connected to positive part of the supply, and TA negative, which is connected to the negative part of the supply. And the output taken from this point, point A, the middle of this leg, as we are going to see later on. Now let's assume I have identical capacitor, hypothetically speaking, because I mean we cannot make sure that it's 100% identical, even if it is coming from the same manufacturer. It's not necessary to be the same. There must be some, let me say, even if small percentage of differences. But let's assume they are identical to give me this voltage separated here half and here half. Let's assume in this way. I want to see the voltage between this point 0 here, the middle of these two capacitor branch, and the middle point of leg A branch. I want to see the voltage between this point and this point. Usually, as I mentioned before, we connect freewheeling diode anti-parallel with the switch, with the thyristor to protect it and to make another path for the current to follow through when the switch is off. Okay. Now this circuit, if the input, if the current following from the input to the output, it means current and voltage at the output are positive, we have inversion mode. If either voltage is positive, negative, as you can see here, voltage is negative, or current is negative, as you can see here, we have rectification mode, energy back to the supply. If both voltage and current are negative, then we have inversion mode, because negative current times negative voltage give me positive power, which means the direction is from supply to the load. Now, let me jump to the output directly. How it look like the output? My input here is DC. How it look like my output here? This is my output. It will be output voltage, which is sinusoidal, as you can see here, and output current sinusoidal, definitely phase shift between them. Most of the time it is inductive load lagging. And as I mentioned, When current and voltage positive, we are in quadrant 1. When voltage and current negative, we are in quadrant 3. And when one of them is negative and one is positive, we are either in quadrant 4 or in quadrant 2. Okay. Still with the definitions, now I will define carrier frequency to be Fs. Carrier frequency is a carrier signal. It's output like this one. Its frequency is high, talking about most of the time in kilohertz. And F1 is the modulating frequency. My output here, as example, this signal, the frequency from here to here, let me say 50 hertz. The output frequency of the output voltage is the fundamental frequency. Now, if I defined Fs, which is high, on F1, which is small, then I will have MF. MF defined to be frequency modulation. Frequency modulation. I need some parameters to judge, to analyze my inverter. So frequency modulation. Now, usually this MF expected to be in the range of 20 plus minus 30 in this range, because as I mentioned here in kilohertz, here in hertz, so the value is high. Another parameter, which is MF. You see M for modulation, here for frequency, here for amplitude. Amplitude modulation is the comparison between control signal and triangle signal. Just a minute, it's remind me with our discussion for pulse width modulation in DC-DC converter. You remember book converter? When we discussed there is a carrier signal, there is a control signal, we compare them between them in the comparator until we get the control on the pulse modulation, let me say, or width. Now, when V control, we make the comparison this way. When V control, okay, a greater than V triangle, then TA will be positive, will be conduct. So this voltage, which is VD over 2 here, will appear here. So here in this direction, VD over 2. Let me change the color. You see here, VD over 2. When V control lower V in the triangle, the second switch will conduct. Now this point, which is 0, connect here. The opposite voltage, opposite of the voltage, which means that minus VD over 2. Now have a look here. Have a look here. This is the triangle signal, the carrier signal, as you can see here, sawtooth. Okay. And my V control, the control signal, I assume it to be sinusoidal because it's supposed to be similar to the output signal. If I want sinusoidal, I have to put sinusoidal. Now, have a look. Let me take example about the comparison. When this is V control here, okay, it's greater than V triangle. So in this period, okay, we have positive pulse, VD over 2. In this small period, let me take another period. Let me take this small period. This point and this point. This is small one. You see here? Now V triangle greater than V control. So I have negative voltage, as you can see here. Negative voltage. Now it's worth to mention here that the fluctuation of the voltage between minus VD over 2 into VD over 2. And also I'm still talking about the situation where my V control lower than the peak of my control signal is lower than the triangle. When it will be higher than the triangle, we'll discuss it in the next slides. But when I mean higher than triangle, it means the output, the control signal will be higher here. You see, the peak here is higher than the peak here. Now, since the control signal is lower than the peak of control signal is lower than the peak of a triangle signal, we call it MA lower than 1 because it's ratio. Where is it? Here, ratio. Lower than 1. And this is what we call it linear modulation, the normal one. And also, it's worth to mention that we will have harmonics. Now, yes, I said here, this is what I'm looking for, to have sinusoidal, to bend this DC, bend it in this way, and make it sinusoidal. But it is not direct and easy. We will see that my waveform will be highly distorted, contain much harmonics. We will have some circuits as a makeup circuit to smooth it, to modify it, to make it more close to sinusoidal, as I will explain. Now, my harmonics here is plotted the ratio, okay, of the peak of the fundamental to the input voltage, comparing with the frequency, the harmonics. We will plot it in terms of frequency modulation, MF. It means MF, 2MF, 3MF. But we can see there is some band side harmonics. Okay, sorry, sideband harmonics. As you can see here, this is 1, 2, 1, 2, 3, 4. There are many sides harmonics. Now, for linear modulation, when I talk about MA lower than 1, linear modulation. Now, the peak value can be found, or the output voltage can be found in this way. Have a look. The voltage for V control lower than V triangle, as explained, the input voltage times the comparison between control and triangle. And since V control is a sinusoidal waveform, it is maximum value sine omega 1t. Then when we substitute this here, we got V sine omega t, as you can see here, and V control triangle, V control divided by V triangle, as you can see here, will give me MA according to the definition. So what this tell me? This tell me that the fundamental voltage, the output fundamental voltage, is MA, forget about sine just to give me this waveform, times half the voltage for half leg, for one leg, half bridge. This is in the case of linear modulation. Also, as I mentioned, we have sideband harmonics. We saw them. The harmonic spectrum is a growth, okay, and have many harmonics. How we can find their harmonics? We can't find them in these two formulae. This is the frequency of harmonics, which is give J MF plus minus K. K is a constant, as I mentioned before, integer constant 1, 2, 3, 4, and so on. And F1 is the fundamental, while the harmonics itself is MF plus minus K. Now, harmonics MF should be an odd integer. MF should be an odd integer. Don't forget, MF is a comparison. MF is a comparative between Fs to F1. It could be 20, 21, 22. Now, it's supposed to be odd integer. Why odd integer? First of all, I will talk about odd or even, about fraction, not in integer. I mean, here integer, it means 21, not 21.5. We will talk about the decimal point, why we don't want decimal point in the next slide. But odd, to make sure that the even will disappear. We cancel the even from the signal. For that, we look to the odd. Now, this is the control signal, as you can see here, and this is the triangle. If I zoom the part here, as you can see here, this is the control again, and this is the triangle. When the control here is higher than the triangle here, we have pulse. When the control here is lower than the triangle, we have negative pulse, and so on. So we get the output. For harmonics, we have table for single phase inverter. We can use it to calculate the sideband harmonics. It's important to know what are these sideband harmonics and what are their values. You may say, why? Because we want to have filter, to cancel them, to reduce them, to attenuate them, to mitigate them. How can we do? Using this table. Have a look. Have a look. Let me explain the table and I will use it in the next slide, an example. Now, the horizontal here is MA. You can see here 0.2, 0.4, 0.6, 0.8, 1. And the vertical here is the harmonics, the fundamental one, MF, MF plus 2, MF plus minus 4, and so on. You need to know what is your MA. Let me show you in the next example. I will back to this table. He told me here half bridge inverter, the one I just been discussing. VD is given to you, the input voltage. Amplitude modulation, MA, is given to you. Frequency modulation, see here, frequency modulation, it's high, and it's 39, which means it's odd, great. And the fundamental frequency, F1, is 47. Calculate the RMS. RMS, it means I will divide by square root, the maximum divided by square root, as you can see here. RMS value of the fundamental frequency voltage and some of the dominant harmonics and some harmonics. Usually we calculate the fundamental and some harmonics. Usually you focus on the near, let me say, or closest or lowest order harmonics close to the fundamental. Now, since it's half a bridge, my output will be VD over 2. I divide it by square root 2 because I want to find the RMS value. Then I need the ratio of the peak output voltage to the input voltage. From where I got this value? By the way, these two, I multiply them because VD is given to me, I got 106. But this ratio, from where I got it, let me back to the table, from the table. All these values represent the ratio, but I need to select the correct one. Now let me go to this example. He told me about the fundamental. Fundamental, just a minute, before I go also, MA is how much MA? 0.8. Let me back. So I will select this column because MA is 0.8, as you can see. Since he asked me about the fundamental, the ratio is this value, which is 0.8. I will say, okay, 0.8 times 106, it gives me this voltage at the fundamental frequency, which is 47, as given in the question. Now, next, I will find the sideband harmonics, find around 5 values, okay? Now, see how we find them? As example, MF, MF plus minus 2, MF plus minus 4, and so on. For MF, as example, which is 39, how much MF? 39 in the question. Okay, 39 multiplied by the fundamental frequency, which is 47, it means 1833 hertz. This is the frequency. But tell me about the voltage. The voltage is 106 again, multiplied by the ratio. From where I got the ratio, I back to the table. This is the table. 0.818. It is equivalent to the frequency modulation MF, which is 39, as you can see here. What if I want to find the MF plus minus 2? I will say, okay, how much MF? MF 39. Plus minus 2, minus 2, it will be 37. Plus 2, it will be 41. So I will find at 37 at 41. 37 times 47, the fundamental frequency is the frequency here. And 41 times 47 is the frequency here. Now, next is to find the ratio. You see here, still 107, 106, 106, but what is the ratio? Let me back. MF plus minus 2. Oh, the ratio is 0.2 to 0. As you can see here, 0.2 to 0. So I got the individual harmonics for the fundamental, for MF minus 2, for MF plus 2, for 2 MF plus 2 or minus 2, as you can see here. You can do and find more and more. And as you can see here, the value will be different from each one of them, and it's increase or decrease depend on the frequency. Now, another situation, I talk about MA lower than 1. There is another situation, MA greater than 1. What does it mean? Don't forget, MA equal V control, over V triangle. And when V control lower than V triangle, we have linear modulation. But when V control greater than V triangle, we have over modulation. In over modulation, harmonic reduced, yes, correct. It's non-linear, not linear anymore. And as you can see here, the sideband harmonics reduced. This graph shows me the different modulation form. You can see here MA with respect to the ratio, voltage ratio. Now from 0 to 1, which means MA lower than 1, we have linear modulation, as you can see here, linear. When we move greater than 1, MA greater than 1, we started with over modulation. You see, we have curve. We have curve. We continue with it until we reach here at the point pi over 4. Why pi over 4? I will show you in next slide when we reach what we call a square wave. So I have linear modulation, I have over modulation, I have square wave modulation. Now, also a few points worth to be highlighted here. One of them is your circuit, the characteristics of the circuit specified by MF and MA mainly. So if we deal with the small MF, now you may say, okay, small, how much small? Lower than 21, they call it small. Greater than 21, they call it large, right? Now, when we deal with a small MF, we have here, we need to synchronize the pulse width modulation. What does it mean? Let's assume this is my triangle, okay? Okay, and then start here. Let me stop here. I will change the color. If my control signal start together, and finish together here, then what we have synchronization. They start together, one control signal equivalent to 1, 2, 3, 4 triangle signal. But let me change the color. If it starts here as example, but finish here, okay, they didn't finish together, okay, then they are not anymore synchronized. We don't want synchronization between the triangle and the control signal. You may say why? Because harmonics will increase. The subharmonics, or what we call them, there is another name for them, subharmonics or non-integer harmonics, fraction of harmonics. These are undesirable harmonics, because you know why we want them integer? Because if we know them as integer harmonics, we can easily manufacture our or design our filter to cancel this. As example, I designed to cancel the third harmonic, the fifth harmonic, exactly for one. But with a fraction, it will be difficult to be predicted, difficult to be cancelled. Still, we need to make sure that odd harmonics is there, so to cancel the even. But when we deal with large MF greater than 1, okay, now harmonics, band side harmonics will be reduced, sideband harmonics will be reduced, but at the same time, what happens is we still prefer to deal with synchronous signals. We don't want asynchronization between the control and the triangle signal. For overmodulation, MF, also the overmodulation means MA greater than 1. And my voltage fundamental greater than VD over 2 as explained in the previous graph, and lower than 4 over pi, because when we reach 4 over pi, it means we reach the square wave inverter. In overmodulation, these harmonics, small harmonics, will disappear. It's not that much problem, similar to the linear modulation. For square wave, we will get square at the end in this way. I explained it before. In this way, we get square. Okay. Now, this signal, the harmonics is also less, and it's easy to bend these lines to make them sinusoidal, as I will explain later. Okay. Now, when I integrate to find the voltage, I will find it is VD over 2, but multiply by 4 over pi, because this is square. When integrate, it will give 4 over pi. Now, from here, 4 over pi came. This is the square wave. In another way, we can explain it in this circuit here. As you can see, when this is the switch Q1, Q2, and these are the freewheeling diode, and my load here between the middle of the line and here the point 0. Okay. When this switch is conduct, the voltage apply here and follow in this direction. V input, which is Vs over 2, will appear across the output. When, let me change the color. When this switch is not conducting anymore, and Q2 will conduct, this one will conduct, then this voltage will follow in this direction, the opposite direction. So we will have the opposite voltage. So we go to from DC, AC square wave. With some filters, we can make it, let me say, sinusoidal waveform. Now for the current increase, decrease, and so on, we can see that increase Q1 will conduct the positive side. And when it's decrease again, diode D2 will conduct this one. Because most of the time our load contains inductance. We need another path for release energy from the inductance to follow through. And when negative, Q2 will conduct. When decrease again negative, then we have D1 will conduct. So always one of the switches or one of the diodes will make a path for the output. Now, the output voltage here is a repetitive waveform, square repetitive waveform. We can represent it in sinusoidal waveform, sinusoidal form by Fourier. We explained Fourier before. It's average plus summation of cosine element, sine element. And since it is, let me say, odd, okay, the one of them will be cancelled, and the only sine element will be there. Cosine element will be cancelled. So only the average, as I mentioned, plus the sine element B of the sine element represented by the integration of the signal to be integrated from minus pi over 2 to pi over 2, full period, okay? And it will be integrated, so we go at 4 over pi, as you can see here, 4 over pi. Also, the output voltage, the final form, after I did this and substitute everything here, will be 2Vd over pi sine omega t. Now, if I want to find the harmonics, the fundamental, I substitute, I got V or output fundamental is 0.45 Vd. It's remind me this 0.45 with single phase half wave rectifier. It was also 0.45 the input voltage. If I want to find the current, then I multiply by Z because it's AC. That is, as you can see here, square root of r square plus omega l square. And sine, it's supposed to be omega t minus the phase shift, theta, which is tan inverse omega l over r, as we explained before. For the output voltage, since it's AC, we have output power, output voltage, output current, cosine the phase shift between current and voltage, or I square R or V square over R, similar to AC discussed before. One more issue to be discussed later on, inshallah, in details in the next session, is the DC supply current. Yes, I want to convert my DC into AC, but expect that you have harmonics on the output and on the input. We need to have filter on the output and the input. We need my load to receive pure sinusoidal waveform. For that, filter is there. And we want to make sure that we don't inject back harmonics into the supply, because other loads connected to the same supply, they may hurt. We need to focus on this. So if we assume that my circuit is lossless, input power equal output power, V input, I input equal V output, I output, I can here, let me say, I can substitute and simplify, because I have output voltages, as I showed there, which is sinusoidal voltage, sinusoidal current, okay? Then I do the integration. I will find that the current, the DC current, will be constant, because VO1, VS, IO, theta is constant. All of them are constants. I will stop at this point. I will stop at this point. We will continue in more details today. Just I